Good evening, everyone. Is there anything that we should look at on the chain rule that we did last time, perhaps? I have a couple of announcements while you think. One is that according to the current schedule, we will have opportunity to meet in person beginning on Monday. So as long as you're feeling well and haven't been recently exposed to COVID, you can come to class. So in person is available Monday. If you signed up for online only, then there may not be enough seats, because this is a large enough class. I don't think we have a classroom. Actually, no, I'm sorry. We may be able to. We've got a larger classroom. Look on the syllabus, and I believe. So if you're signed up for online only, but you really want to show up in person, send me an email, and probably I can let you in, because I think we have enough seats to do that in the big room we have. All right, in person is available on Monday and afterwards. The second thing is I was going to give an extra credit quiz today just to try out the email, but I need to move that till Monday with some things that are going on. Monday we'll give the extra credit 10 points. Some short question out of sections 13.1 through 13.5, something out of there, just for fun. This will be practice for the test when we'll have to do that by email. What I do is I'll send out by email the quiz, print it out or look at it on your phone, write it on blank paper or write it on the printed out version. Either scan it and send it to me, or take a picture on your phone and send it to me back at the same email. And if you're here in class, you can take it in class, and if you're at home, you can take it by email. Okay. That means if you come to class, bring your books and notes, because it's open notes, open books. But it's just an extra credit. You probably won't need much of them. Bring books, notes, if coming to class, so you have all your things you need here. I'll try and make it so a computer isn't a big advantage. All right. First test, however, will be not in person. We'll stay home for that one. Everybody will get it by email. All right. No questions yet?
Actually, sir, on number 29 from 13.5, my answers were much bigger than the back of the book's answers.
I'm sorry, I couldn't hear very well. Say again?
On number 29 from 13.5,
yeah,
like I got really long answers, but the back of the book were relatively short.
Okay, let's see that one. Here's the problem for review then. This stuff you just have to practice at it, really. Suppose W is 4x squared plus 4y squared plus z squared, and x can be written in terms of new variables as rho sine phi cosine theta. Y can be written as rho sine phi sine theta, and z is rho cosine phi. They're all up there, I'm sure. I'm going to move it over just a bit. Oh, it's okay, isn't it? All right. Then the question is, find dw, d rho, dw, d phi, and dw, d theta. Maybe we'll just do part of this. dw, d rho. Here's what you can do. If you think of that picture they have in the book, you have w is a function of three variables, x, y, and z. think probably what happens is just some trig simplification on this. And by the way, this actually is a significant problem here because these coordinates here are called spherical coordinates. And we'll talk about these more in the semester, but this is saying, suppose you convert this function of x, y, z to a function of spherical coordinates in this new coordinate system. What's the rate of change in w with respect to this variable rho? All right, so w is a function of x, y, z, and each of these is in turn a function of rho, theta, and phi. So you can get a pretty complicated chain rule if you get too many levels of too many variables. What is dw d rho? You take all paths down to rho, and you multiply all the partial derivatives along the path. So I didn't write them all, but this would be dw dx on the path from w dx. From x to rho, you put dx to rho, and so forth on all the branches here. So you'd say dw d rho coming down this path, or it is coming down this path, dw dx. Oops, dx d rho, I should have put. Plus, I come down this path to rho, dw dy, dy d rho. And then I can come down this path, dw dz, dz d rho. You don't need to draw the tree. It's just, once you've done this for a while, then you figure it out. And now w, dw dx, these are treated as constants, so dw dx is just 8x. Dx d rho, these are treated as constants, so it's just 1 times sine phi cosine theta. Then over here, dw dy, this and this are treated as constants, so it's just 8y. dy d rho is 1 times, this treated as a constant is sine phi sine theta. And then dw dz is 2z, right? Plus nothing, because treating the other two variables as constants. dz d rho, partial with respect to rho, that with phi held constant is just 1 times cosine phi. So there's the partial with respect to rho. Now you have to put in what x, y, and z are, because the idea is that really w is a function of these three other coordinate variables, rho, theta, and phi, just with x, y, and z intermediate.
Will those trig parts not be squared?
No, because I'm just taking dx d rho, so I take derivative of x with respect to rho. So here's dw dx, just saying this function of x, take a partial derivative. Here's dx d rho, just look at this one and take derivative with respect to rho. That's all I did.
Okay, thank you.
Okay, and now x is actually rho sine phi cosine theta. So this is 8 rho sine phi cosine theta. And it multiplies this sine phi cosine theta. And then over here I have 8y. Put in what y is. This is 8 times rho sine phi sine theta times sine phi sine theta that was already there. And now I do need to move it a little bit. Hopefully that's okay. Sometimes it's hard to see on here. Plus dw plus 2z, which is 2 rho cosine phi, times cosine phi. So here's 2z, and then times cosine phi. So I just put in what x, y, and z were. And now what happens a lot of times with these spherical coordinate problems is trig identities simplify it a lot. That's probably where a lot of the trouble is going on. Let's see. These both have a factor of 8 rho. And let's see, this one is 8 rho sine squared phi, right? This one is 8 rho sine phi times sine squared theta. Maybe I should write them out, just make it clear. So I'll write out intermediate steps. 8 rho sine squared phi cosine squared theta when you multiply this one. Right? This one, the next one is 8 rho sine squared phi sine squared theta. And the last one is 2 rho cosine squared phi. Now you notice on these, you have an 8 row sine squared and an 8 row sine squared. This one times cosine squared and this one times sine squared. Well, if you combine those, you can call them 8 row sine squared phi by the distributive property, all times cosine squared plus sine squared theta. So I'll combine those two, right? This times this gets this one, this times this gets this one. And then plus 2 row cosine squared phi. Now, this is 1 by the Pythagorean identity of trigonometry, so you've got 8 row sine squared phi plus 2 row cosine squared phi. Now you've got a common factor of 2 row in there. You could factor it out. You could call this 2 row times 4 sine squared phi plus cosine squared phi. This would be a good answer. I would take this. If you want, you could combine one of these sine squared with the cosine squared and call it something like this: 2 row times 1 sine squared plus cosine squared is 1. And then you got 3 sine squared left over. So 3 sine squared phi plus 1. That would be a good answer too. They're both about as simple. This one's a little simpler, maybe. I don't know which one the book put. Now you do similarly with the other ones. I guess let's just do A. Unless, if you really want, we can do B.
No, you're fine. That's funny. Thank you.
Okay. Yeah. So part of the trick here is trigonometry, actually. All right. Put it back at the other end here.
I have a quick question about the extra credit for Monday. Is that like we have to take it within 20 minutes, or is it like an all day sort of thing?
No, it'll be, yeah, it'll be 15, 20 minutes. It's not a long one. That's why it's a quiz.
Okay.
But just right at the end. Well, we're going to get on now to directional derivatives, right? We have partial derivatives to get the slope of the tangent line in the direction of the x-axis and the direction of the y-axis. What about a derivative in any direction? That's this one, as the name suggests. And we started this just a little bit last time. I want to remind you, it's been a while. I can do a little better presentation with a little more time here also. Let the directional derivative of f of xy at the point x0, y0 in the direction of u with components, let's say u1, u2, be the following. We'll take the derivative with respect to t, which we also write as a limit. Derivative with respect to t of f of x0 plus u1t, y0 plus u2t, evaluated at t equals 0. Let's do it that way. That'll be the definition. We won't actually compute anything from that, but I'll box it just because it's the definition. And we can give it this notation, d u f at x0, y0. Then we have the following theorem that results. We can apply the chain rule, right? To take the derivative with respect to t, I could think of this as, let's call this v, and this w. So it's f of vw, a function of two variables. If we want d dt of f of VW with respect to this secondary variable, right? These are constants, x0, u1, y0, u2. We can take the chain rule, right? See, the chain rule's got an immediate application. The chain rule, df dt, thinking of function f as a function of t through these intermediate variables v and w. So we put, here's f, it has variables v and w, and each of these are a function of t. So we put partial derivatives on this one, df dv and df dw. And here is dv dt, ordinary derivative, because it's only got.
Excuse me, please could you adjust the camera?
Say again? Move it over?
Could you adjust, yeah.
Yeah, I thought I just got the edge. I guess I just missed it. Thank you. Appreciate you letting me know that. Yeah, so there's the tree. And so we go down this branch to t or this branch to t, both of them get down there. And we just multiply the derivatives along the path. And we can say, oh, this is df dv dv dt plus df dw dw dt by the chain rule. Now let's see, df dv, I can just leave it like that. Let's call it df dv and, well, all right, let's df dv. And then dv dt, v is x0 plus u1t, so it's part, these are constants, so its derivative is just u1. Right? And then over here we've got df dw. Times the derivative here is just u2. But now wait a minute. Maybe I shouldn't even call those v and w, because after all, the idea is that f is a function of x and y, and I'm just letting x be this and y be this. So I could change this and call it, where's it done that in the first place? Df dx down to x and df dy down to y, where x is x0 plus u1t and y is y0 plus u2t. And so this is dx dt and dy dt and df dy and df dx. And so I can really write it this way: ddx and dx dt, ddy and dy dt. It looks like that. And so this is df dx times u1 plus df dy times u2. And what is that? That is this vector of partial derivative, df dx, df dy, dot product with the unit vector u1, u2. And I should have said that up here. In the direction u1, u2 is a unit vector. You can take the derivative with respect to non-unit vectors, but if you say directional derivative, it's simply a vector. All right, so that's it. Now, if we define the vector of partial derivatives there to be called the gradient of f. So the gradient of any function of two variables is just the vector of partial derivatives. And you can extend this to functions of more than two variables also. So it's the f dx.
Can you move the camera again?
Yeah, the f dy. Should zoom it out just a little bit. Maybe we can get a little bit more. If I make this definition, and I've already let u equal u1, u2, this is the following theorem, that the directional derivative, by its very definition, just write down the chain rule, derivative with respect to f at x0, y0 is the gradient of f dot product with u. Gradient of f at the point x0, y0 actually, dot u. Because really, after we take the partial, this is why I started writing v and w. After we take the partial derivative, it has to be, or when we take it, it has to be at the point x0, y0. All right, so this is what it comes out to be, but x0, y0 is any point I want. So since this applies for arbitrary x, y, I did that just to show you can treat them as constants there. The partial derivative with respect to f at any x, y is in the gradient of f dot product with the direction you want it to go. We can call that equation 1. That's how you evaluate this directional derivative. And then a note we made last time also, if u is the unit vector I, component 1, 0, so this is what we also call I, the unit vector along the x-axis, then the directional derivative is what? By this theorem, duf is gradient of f dot, well, the gradient is df dx, df dy. And we dot product that with the vector 1, 0. What do we get? We just get df dx. So the directional derivative in the x direction is just the slope of the tangent line in the x direction. And similarly, if u is the unit vector in the y direction, 0, 1, then duf is equal to df dx, df dy, this time dot the vector 0, 1, which comes out to be 0 plus df dy. And so the directional derivative coincides with the partial derivatives in those directions. Now what it really does is it gives you the slope of the tangent line in any tangent plane in any direction. We're going to find out. So really, geometrically, this is what's happening. I'll just give it a lead in without actually showing it at this point. But if you have a differentiable function so that you can construct a tangent plane at any point x0, y0 in the xy plane. I'll write it with 2 coordinates since I'm in the xy plane, but really, I mean, it's sort of x0, y0, 0 if you prefer. Put it down here. What the directional derivative does is it gives you, if you're moving in the direction u, a unit vector, it gives you the slope of the tangent line in that direction. In special cases, the slope of the tangent line in the x direction is df dx. Slope of the tangent line in the y direction is df dy. So that's what it does. It gives you the slope in this direction. Over this vector. Let's see if we can compute some of these then, just for practice. This is what some of the homework is going to be like also. That's just the one we just did. Suppose I have this. Suppose I have f of xy is the sine of 5x minus 3y. This is number 2 out of the homework, out of the problem set. And at the point 3, 5, so they put P 3, 5, that means the point with coordinates 3, 5. Books list these differently. Sometimes they'll put P 3, 5, meaning the point with these coordinates. Sometimes they'll put point P colon, or sometimes they'll put P equals, since there's a one-to-one correspondence between the points and the coordinates, whichever way you like to put it. So it's the point with coordinates 3, 5 in the direction of u equals 3/5 I minus 4/5 j. find the directional derivative, duf, at that point. I'll erase this. What you do is you just apply the theorem and say by one with the gradient, the vector partial derivative. So it's the gradient of f(3,5) means take the gradient and then plug in 3,5, just like you can take a derivative and then plug in the point. So this is the vector df dx, df dy, then plug in the 0.35. df dx, well, what's the partial with respect to x of this thing, right? I can compute it on the side here. df dx is, well, if we think of this as a function of one variable u, right, we can say that's df du dx. It's the chain rule, or the first function, f is a function of u, and u is in turn a function of x and y. So it's ordinary derivative of f with respect to u, and then partial derivative of u with respect to x. I don't know where to write that. To get down to the next level. There's the chain rule for df dx in this case. So we'll say derivative of sine u is cosine u. And then du dx, treating y as a constant, is just 5. So this is all 5 times cosine 5x minus 3y. So I'll put that in here. 5 cosine 5x minus 3y. Now you can probably guess it at this point. If I take partial derivative with respect to y, I've got d sine u du dy is still again cosine u, but then times minus 3. So this is going to be minus 3, analogously, 5x minus 3y is df du times du dy is minus 3. So there it is. Now, we want to evaluate that, however, at the 0.35.
Can you move the camera a little more, please?
Yeah, okay, thank you. Shoot. Gonna keep you guys awake, I guess. All right, 3,5. So this is 5 cosine of 15 minus 15 is 1. Cosine of 0 is 1. Minus 3 cosine 0 is 1. The gradient at this point is just 5 minus 3. And then u is already given. So we'll say, maybe I should write this on the opposite end. I hate to, but I guess I better get some room. We said by equation 1 with that gradient and the given u, now du f is gradient of f at 3,5 dot u was, oops, sorry, 3/5 minus 4/5. And this one was 5 minus 3. Let's see, we get this times this plus this times this. Gives me 3. This is right, plus 12/5. I guess it's 27/5. So there's the directional derivative. That would be the slope of the tangent line moving in that direction. Yeah. Now there's a really neat theorem that comes up following this. You think, oh, the gradient is just a nice little tool for computing the directional derivative, but it's actually much more than that. This formula tells you something quite powerful through the following theorem. Since the largest directional derivative since the directional derivative is duf equals gradient of f dot u. The dot product is the length of the gradient times the length of u times the cosine of the angle between them, right? That's the value of that dot product. Theta equals the angle between. What's the largest it can be? Well, this is fixed, right? The gradient at the point is just a fixed number. This one is equal to 1. So this is equal to the length of the gradient times the cosine of the angle it makes with theta. What's the biggest this can be? What's the smallest? The largest directional derivative, this would be the first point, occurs when theta equals 0. So you get 1 times this. That's the biggest cosine theta can be. In other words, if u points in the direction of the gradient, so if you want to know what's the largest slope of a tangent line, the largest slope of the tangent line occurs in the direction of the gradient, and its value is equal to this times 1. That's the largest slope possible. There are important algorithms. There's one called the method of steepest descent for solving problems, like if you have intersecting surfaces or something and you want to, or maybe you want to find the minimum of a surface. Here's a surface like a drumhead or something, and it's vibrating. And you start at some point and you say, I wonder where's the minimum on the drumhead. You want to take your steepest slope down to the bottom here. What you do is you take the gradient to go down as quickly as possible. You go to here, and then maybe you go to here. And it's kind of like Newton's method that you saw in Calculus 1, I think it was, except for surfaces. And so the method of steepest descent, and there's other methods too in physics. The gradient is often is how you tell the direction of force is pointing. You take the potential, and the gradient of the potential tells you the direction of the force, or minus the gradient of the potential, depending on which way you define it. It's usually minus the gradient of the potential in physics. But see, the gradient has that immense importance then for telling you which direction a force is going to point, for telling you what's a numerical algorithm to get to a minimum as quickly as possible, or at least in a quick way. And what this theorem tells you here is that the largest directional derivative is if you point your unit vector u in the direction of the gradient, in which case the slope of the tangent line, or the gradient itself, is or the directional derivative is the length of the gradient vector itself. What about the smallest? Now, taking negative numbers is smaller than 0 and smaller than positive numbers. The smallest occurs when cosine theta is -1. That's when you point theta at pi radians, 180 degrees. So the smallest directional derivative occurs when theta equals pi radians. It's opposite the gradient, the point direction minus the gradient. And what's the slope in that direction? Well, it's minus 1 times the length of that when you put in theta equals pi. The value of the directional derivative then is minus the length of the gradient at the point. And then the book puts a third point. If the gradient at the point happens to be 0, 0, so the gradient at whatever point x0, y0.
Does that say negative in front of the length?
Yeah, I wrote a negative. It doesn't show very well, does it? Yeah, it's minus. Yeah, thank you. Looks like one of these scratch marks, doesn't it? But you know, I started off the day, this thing is pristine and everybody can read everything. And by the end of the day, it's a cloud. All right. It's worse if I use these regular erasers too. Okay, now if the gradient of f happens to be 0, the 0 vector at the point, then all directional derivatives are 0. And the intuition for this is the following. In that case, you've got a horizontal tangent plane, right? The slope in all directions is 0. All right, how do you know that? Because if you take the 0 vector and dot it with any other vector, you always get 0, right? So that's the proof. You just take directional derivative is gradient of f dot u. I don't know if you can still see this. I think you can. 0 vector dot anything is 0, so all the directional derivatives are 0. Maybe I should write that in. This is a vector 0. This is the number 0, right? Dot product of vectors is a number. Gradient of a function is a vector. Anyway. So some of the problems ask you to do that, and I've given you a lot of problems out of this section actually, because there's a lot of different kinds of things in here. They aren't all that hard. There's just a lot of concepts. Suppose we look at this one. F of x, y is equal to x over x plus y. And at the point P with coordinate 0, 2, find the direction in which f increases most rapidly and the rate of change in that direction. Just what I showed you on the mountain picture there. Find the direction in which f increases most rapidly. And that rate of change. I was getting tired of writing already. All right. Maybe I can just move over a little and still be on camera, I think. Well, you take this last theorem to heart and you say, the direction is the direction of the gradient. So we need the gradient. The gradient of f at an arbitrary xy is just the vector of partial derivatives. It's really easy for such an important vector, right? So
Excuse me,
f.
what did you write after that rate of?
Oh, that rate of change. I told you my head was getting tired. Yeah. That rate of change of f. Yeah, it's hard to read.
We can't see what you just wrote.
Oh, it's still off the edge? I'm sorry. I thought I had the thing just over far enough. That worked, there we go. Now, if the other part's only still on, oh, all right. Maybe. Okay. From the gradient is the vector of partial derivatives. We just compute them. What's the partial derivative over of x over x plus y? Well, we can calculate on the side d dx of x over x plus y. This is a quotient, so we can use the quotient rule, right? And here's the quotient rule written as partial derivatives, right? It's, if you think of this as u over v, it's v u prime minus u v prime over v squared, right? It's the same rule, it's just you write partial derivatives. So it's v x plus y times u prime, but prime means d partial derivative, so it's dx dx, minus u, which is x, partial of the denominator, d dx of x plus y over the denominator squared. So there's a quotient rule for partial derivatives. V u prime minus u v prime over v squared, but the prime is get replaced with derivative with respect to x, right? Partial derivative. So I've got x plus y times 1, right? Derivative of x with respect to itself is 1. Derivative of x plus y with respect to x is also 1, right? Because y is treated as a constant, 1 plus 0. So this is x plus y minus x is just y. And then that's over x plus y squared. Now we also need d dy of x over x plus y, and this is going to be a little different. The same concept. So it's v x plus y u prime dx dy this time minus u, which is x, v prime, which is d dy of x plus y, all over v squared, x plus y squared. Well, this time dx dy is 0 because, right, x is treated as a constant. Derivative with respect to y of x plus y is 0 plus 1. This is 1. So it's just minus x over x plus y squared. So I've got for the vector of partial derivatives here, y over x plus y squared minus x over x plus y squared. There it is. But I don't just want that one. I want it at the point 0, 2. So I compute the gradient and then I plug it in and get the gradient at 0, 2 is therefore 2 over 2 squared and 0 over something is still 0. Right? So it's 1/2 0. Is the gradient. Because of that, now the directional derivative.
Can you put it back a little bit more to the right to see the
Okay.
board?
Yeah, as long as you can see the rest of the board, I need to go to here.
Yeah, that worked. You just a little bit.
Okay, thank you. By that, we now say, what's the directional derivative in the direction it increases most? The direction of steepest increase is that of the gradient. So I take u to be the gradient vector at that point. Well, that's not a unit vector. So how do I make it a unit vector? Just divide it by its length, right? You take any vector, any non-zero vector divided by its length is the unit vector in the same direction. So we take the gradient divided by its length to find the proper direction for steepest increase. And let's say we got 1/2 0 for this one. And we'll divide it by the length of 1/2 0, which is 1/2. It's just the vector 1, 0. So it's increases most steeply in the x direction. Now we can find the directional derivative. Well, we can take gradient of f dot u and compute the derivative in that direction of steepest ascent by that theorem. But what's an easier way than computing the directional derivative from the theorem? Well, from the first theorem. The last theorem says that the value of that directional derivative is actually the length of the directional derivative itself, the length of the gradient itself. So it's really, to calculate this, you don't have to recalculate anything. You just have to take what is the length of the gradient. This is the steepest slope. And so, it's the length of 1/2 0, it's just 1/2. So the steepest slope is in the direction 1 0 x-axis, positive x direction, and the slope is 1/2 in that direction. Suppose I asked you now, what's the direction of steepest descent, steepest decrease? And what's the smallest slope? Somebody knows this one. This is the direction of steepest ascent up the mountain. Direction of steepest descent, we said, is exactly opposite. Now you go downhill with the same slope, minus 1/2. So the direction of steepest descent is just minus u, which is minus 1 0, backwards along the x-axis, with slope in that direction, d minus u f at 0 2 would be minus 1/2. Now there's a very interesting theorem that comes along in addition. Recall we did level curves. On top of this, the geometry of the gradient has a nice interpretation with level curves. As this result, f has continuous partial derivatives in a disk or any open region, since every open region in topology is the union of open disks. In an open disk, or open region, centered at the point x0, y0. So no matter how small, just some region.
Excuse me, before we go on, for the negative u, did you only multiply x by -1, or because y is 0, so it doesn't need, like, do we multiply x and y by -1?
Not sure I understood the question. This was the direction in which you got the steepest slope, so I just took minus this vector, so minus both components. -1 minus 0 is minus 1 0. And that's the direction of steepest descent. What you have is something that looks like this. At the point 2 0 in the xy plane, it should be along the x-axis. Something like that. Let's see. I guess the curve looks more like this. So here's z equals f of xy. If you move in the positive x direction, you get a tangent line looks like that. And the slope of the tangent line is duf at 2 0 with u equals 1 0. Gives you slope equals 1/2. But if you go the opposite direction, down, so this is the direction 1 0. In this direction, it's uphill at 1/2 slope. If you go in the opposite direction, minus 1 0, then you get the steepest downhill slope, which is slope equals -1/2 in that direction. I mean, it's the same line, but if u points in this direction, say the slope is this, is rising. If u points in that direction, it's going down. Did I answer the question? Or maybe I answered the wrong thing.
Yes, you do.
Okay. So that's the idea. All right, if it has continuous partial derivatives, then the gradient of f is orthogonal to the level curve. Sorry, level curve of f at x0, y0. Remember what level curves are. They're the traces you get by cutting the surface with horizontal planes and then projecting them down on the x-axis. So these are really neat to do in MATLAB if you ever program MATLAB. I say MATLAB, but actually MATLAB costs a lot of money. There's a student version that's much cheaper, but best thing for you is to go online and get Octave. I'm trying to remember the name for a second. It's not kind of... Octave is a free version you can download from the new GNU with the G silent. It's like the animal. And this is a free software site that's not copyrighted. You can download all the stuff. And Octave does pretty much all the same things that MATLAB does, making neat surface graphics, works well with matrices and complex numbers, all sorts of stuff. It's a nice programming language for engineering and science. You don't need it for this class. I'll just say, when you see my nice graphics on the syllabus and on other places, I usually made them in Octave or in MATLAB. I used to have MATLAB. So you can make these pictures too and draw these things and see what they look like if you get this and just learn a little bit of programming. It's not too hard if you've programmed in any language before. But what you can do and what Octave and MATLAB have a nice capability for is plotting a surface plot like this, and then it can sketch your level curves and the result. If you cut this with a horizontal plane up here, this is the function, say, z equals f of xy. This is going down back to our first lecture now. This cuts it in what we call a trace, right? Maybe it looks like that. It's the intersection of the plane z equals some constant k with the function z equals f of xy. So this curve is the point f of xy equal k within the z equals k plane. Right? Now, if we take that and project it down at the xy plane, just drop it straight down here, then it's a set of points f of xy equals k in the xy plane instead of the z equals k plane that we call a level curve. And we usually label it with k just so that's the tangent plane that it came from. Then I can intersect it at some other point. And this is what's fun about modern graphics. We didn't have these on. You can intersect it here, get another level curve. Maybe I should call this first one K1. Then I can call, and those are all K1 then. Then I can call this one C equals K2, some other constant. Drop it down in the plane. And what you get then is this topographic map showing level curves corresponding to all these traces being dropped down. Here's the set of all points such that f of xy is equal to K2. And you can do another one with K3, right? And you get a whole bunch of level curves. And then this is topographic map like you see from the geology places and so forth, showing you the isopleths, the level curves you could walk around the mountain on, right? And the theorem here says that if you look down in the xy plane, at any point here, let's say x0, y0, what direction does the gradient point? It points perpendicular to this is what it says. So it's perpendicular to the level curve at that point, here's x0, y0, p with those coordinates. And then the value of the gradient is the slope up over it. So here is slope, slope is the gradient, the length of the gradient at that point. Right, the slope is the directional derivative, but when you're in the direction of the gradient, the directional derivative is equal to the length of the gradient. So that's the idea. If you look down in the plane of level curves, the gradient vector at any point, this would be this vector will be the gradient at the point x0, y0. Is perpendicular level curves and points in the direction of increase. It's perpendicular in this direction too, but that's decrease. So this is minus the gradient this way, plus the gradient this way. Alternatively, if you're over here at this point, x1, y1, then the gradient points perpendicular to that, something like that. And its length is the slope of the tangent line here. So the vector points perpendicular, and the length of the vector gives you the slope. So there's some problems dealing with that then. Find it now. That's some of the homework. Oh, here we go. Suppose I gave you this one. This is 49. Like your homework problem. Suppose f of xy is x squared plus 4y squared. And you're at the point with coordinates minus 2, 0. And I said, sketch the little curve that passes through P. And draw the gradient vector at that point. So the level curve has to go through this point. We'll take f of minus 2, 0 is equal to minus 2 squared plus 4 times 0 squared is 4. So the level curve, that's at the point at P. That's the value of f. So the level curve is f equals that number. F of xy equals 4. Or, putting what f of xy is, it's x squared plus 4 y squared equals 4. And here's where you have to put a curve you can actually sketch. What is the sketch of that thing? Anybody remember?
An ellipse?
Yeah, it's an ellipse. Awesome. X squared over 4 plus y squared equals 1. If I divide through by 4, and I can think of this as y squared over 1 squared and x squared over 2 squared. It's an ellipse with semi-axes 2 and 1, right? Remember that standard ellipse equation? Semi-major axis along the x is the x-axis, or along the x-axis. and centered at 0, 0. So I think this is far enough forward. Let's see. Now it looks like this. Goes out to a 1 on the y-axis and 2 on the x-axis. And at this point, minus 2, 0 right here, the gradient, you can calculate it, but you already know where it's going to point. Gradient of f is the vector of partial derivatives. Partial derivative with respect to x is 2x plus 0 is 2x. Partial derivative with respect to y is 0 plus 8y. So there's the gradient. Now the gradient at the point, minus 2, 0, you just put it afterwards, minus 2 for x, and get 2 times minus 2. Put in 0 for y, and get 8 times 0. So you get that the gradient is actually the vector minus 4, 0. And the gradient then is 4 units long, pointing perpendicular, just as we predicted. So this goes down to minus 6 here. There's the gradient of f at minus 2, 0. Oh, I can't see that, huh? Gradient of f at minus 2, 0. Perpendicular to the level curve because it's a vector minus 4, 0. Now, if we can do that for functions of 2 variables, we can also do it for functions of more than 2 variables. It's just harder to draw because now if I draw w equals f of x, y, z, a function of 3 variables, I need 4 dimensions, so I get w with it. So this all extends to more dimensions, it's just harder to draw. We'll just do it one more dimension. W equals f of x, y, z. And everything here is completely obvious at this point. I need to erase this, I guess. The gradient vector for a function of 3 variables, gradient of f is just a vector of partial derivatives, but there's 3 of them now. df dx, df dy, df dz. And the directional derivative is hard to draw because it's a slope of the tangent line to a 3-dimensional figure in 4-dimensional space. But nonetheless, you can calculate it. duf is again gradient of f dot u. How do you prove it? By the chain rule. You just do the same thing with one more argument. And even if you can't visualize it, you can figure out what it is, right? And as before, the direction of steepest descent is that of the gradient when it's not 0. If the gradient is 0, then it's a horizontal tangent line. All directional derivatives are 0. But the steepest descent, again, for gradient not equal to 0, gradient not equal to 0, not the 0 vector, is the direction of the gradient. I guess I put this on the other side. I moved it over a little bit. How about that? I'll just go back and forth so I don't have to move the camera so much. All right. So it's in the direction of the gradient. And if you want a unit vector, you can just divide the gradient by its length again. It's still this direction. You don't have to divide it if you don't want a unit vector. With slope in this direction and equal to the length of the gradient, just like before. So it all carries over to more dimensions, as many as you want. In particular, here it is in one more dimension. You say, well, who needs this if it's 4-dimensional space? Maybe somebody does space-time or something. Einstein needs it. Actually, it has some other applications too. One application is to finding normal vectors to surfaces in 3 space. So here's an application. Just one of them. Oh, I should put one more thing here, just checking my time. One last note for this application is, just as before, now the gradient of f, there's no more level curves. What do we have if we put a function of 3 variables equal to constant in 4-dimensional space? Or three vectors, a function of 3 variables equal to a constant. Just like here, when we put a function of 2 variables equal to a constant, we got a curve on the plane, right? Here's the curve, f of x, y equals c. What happens if we put a function of 3 variables equal to a constant? It's a level surface of this object in the 3-dimensional object in 4-dimensional space. So gradient of f is now orthogonal. I'll write this perpendicular sign here. Is orthogonal to the level surface level surfaces, which are f of x, y, z equal a constant k when it's differentiable. So you can actually calculate this with continuous partial derivatives. And so when it has continuous partials, which for engineers is usually the case, right? At the point in question. And in a disk. There's an application right here, is if you have a surface, you want to find a perpendicular normal vector to it, the gradient will find it for you. So here's a simple example then. Suppose I have f of x, y, z equals x squared over 4 plus y squared plus z squared. Right? There's a function of 3 variables. And I say, find a normal to the surface f of x, y, z equals 4, right, at the point I think I want square root 8 here, 1, 1 from the, yeah, okay. It has to have a point that's actually on this little surface. Anyway, so suppose you want to find a normal to this surface at this point, you can use the gradient, right? Even though you can't draw the figure, W equals f of x, y, z, you can draw its level surfaces. Just like with surfaces, you can draw level curves to figure out what they look like. All right, so we compute the gradient of f is the vector of partial derivatives. Partial with respect to x is just 2x over 4 is x over 2. Partial with respect to y is just 2y. Partial with respect to z is just 2z. So there's the gradient. The gradient at that point, square root of 8, 1, 1, looks like then square root of 8 over 2, 2, 2 is the vector. Well, this is 2 square root 2, so it's square root 2, 2, 2. Then we can sketch this. What is this? The level surface f of x, y, z equals 4. Since the level surface is x squared over 4 plus y squared plus z squared equals 4 is equivalently x squared over 16 plus y squared over 4 plus z squared over 4 equals 1 is an ellipsoid. All right, this is an ellipsoid. Remember, centered at the origin with semi-axes semi-axis lengths, let's say 4, 2, and 2, the square roots of these numbers. We do similar to the last one, just with the level curve and gradient, just with one more dimension. Now we draw the surface going out 1, 2, 3, 4, 1, 2, and 1, 2. And here's the cross section XY plane is an ellipse with semi-axes 4 and 2. And the YZ plane is actually a circle, right? And you get this kind of an ellipsoid, kind of a hoagie or something. Football. Anyway, all right. And then at the point, square root 8, 1, 1. Square root 8 is somewhere in here. So square root 8, 1, 1, something like that. You can draw yourself a little box of links, square root 8 by 1 by 1. Go out to the corner of the box and say, at this point, here's my vector, square root 2, 2, 2. Coming out of the board here. Hard to draw. It's hard to make this look perpendicular because it's almost right on the board, isn't it? But it's the vector gradient of f. There it is. So that's the idea, is it's perpendicular to the tangent plane of the surface. Here's the tangent plane. And the gradient comes out perpendicular to that. All right, let's see. Got about a minute and a half, so I don't want to start a new section. Any other questions on that? That's about a good stopping point. All right, well, let me leave you these problems then. This will be 13.6. Let's just run a quiz through 13.5, so this won't be on the extra credit quiz. It's probably just one problem because the problems here are too long to do more than one, probably, maybe two problems. 1, 5, 9, 13, 17, 21, 33, 41, 47, 53, and 63. We'll have all these kind of problems we did tonight using the directional derivative and gradient. All right, have a nice weekend.
Excuse me, can we take the